Up until now, we've covered several of the most common inputs that you might see and use: the impulse, the step, the ramp, and the sinusoid. Today, all in one shot, we are going to cover literally every other input that you could possibly have. In order to show you how this works, I'm going to walk you through two special properties that systems can have. These special properties are linearity and time invariance. Let's start by looking at linearity. A system is considered to be linear if the principle of superposition holds. The principle of superposition is an amazingly useful property that gives us an incredible shortcut for predicting the output of a system for any kind of an input. Here's how the principle of superposition works. Let's suppose that we apply not just one input to a system, but more than one input at the same time. Each of these inputs would produce its own output if they were applied separately. The total output of this system will be equal to the sum of the two individual outputs that would have resulted if the two inputs had been applied separately. Another way of saying this is that if we apply to a system an input that is the sum of two other inputs, then the output of the system will be equal to the sum of the two outputs. Let me show you an example. Suppose that we give to a system an input that looks like this. This signal isn't any of our standard inputs. However, we could break this input down into two parts. This weird signal is actually the sum of a sine input and a ramp input. The purple and red inputs together add up to the blue input. Now, suppose that we are using this weird blue signal as the input to a first-order system. How could we predict the output of the system to this kind of an input? The first thing that we will do is we'll find the output to the ramp input. And we can do that using the time constant of the system. So this is the output to the ramp. Next, we can look at the Bode plot for the system and find the gain and the phase to predict the output to the sine. Perhaps we find that the output to the sine wave looks something like this. Now, in order to get the output to the blue signal, we sum up the output, the orange and the green. We add these signals by adding up the value at each instant in time. For example, we'd take the value of the orange response to the ramp at this time and add it to the green. So here's the orange value and here's the green value. The resultant value would be around there. We would do this at every point in time. I'm just picking some random times here to show you what the sum would be. After we've finished doing this summation, the response might look something like this. A sinusoid going up the ramp response. We can use this same approach for any kind of input signal that can be broken down into a set of our standard inputs. For example, we could add together a ramp input and a step input to give us an input that would look like this. We could add together a step and a sinusoid to give us the value of a sinusoid with a DC offset. This principle is not limited to only two signals. We can add together 3 or 4 or any number of individual signals to create a more complex input signal, and we can always find the output to whatever strange input we have by first finding the output to each of the individual input signals and then adding together each of those output signals to get a complete output. Now, perhaps most usefully and most amazingly, we can also do this with multiple sine waves. For example, suppose that I have an input signal that looks like this. This signal is the sum of a low frequency sine wave together with a high frequency sine wave. By recognizing that this signal is two individual signals added together, a low frequency and a high frequency, I can find the output entirely by looking at the Bode plot. For example, suppose I know that my Bode plot looks like this. To find the output to that strange looking signal, I just have to go get 2 points on my Bode plot. Suppose that I know that this frequency is the high frequency used in the input signal. We'll call that omega high. Suppose I know that this frequency is the low frequency that was applied in that signal. I'll call that omega low. Now what I'll do is I'll go and get the gain for the low frequency. I know that gain is equal to 20 times the log of the amplitude of the output over the amplitude of the input. The Bode plot shows that my gain here is 0, meaning that the amplitude of the output and the input are the same. I can plug in 0 for my gain. And I would also plug in the amplitude of the input, which I know because we have the input signal plotted on the plot. Suppose I know that the amplitude of the input is 10. I can then calculate the amplitude of the output by knowing the gain, and I would find that the amplitude of the output is also equal to 10. Next, I go down to the phase plot, and I find the phase at omega low. I see that the phase here is 0. Now, I will start to draw a time signal of the output. I know that the amplitude is 10, the frequency is omega low, and the phase is 0. So the output signal to this one input will be something like this. This is a signal that is at the low frequency. The amplitude is at 10, and the phase is 0. I've drawn it so that the inflection point crosses 0. Next, I'll go back to my Bode plot, and this time I'm going to get the values for omega high. I see that at omega high, the gain is negative 20. Let's suppose that I know that the amplitude of the input here is 1. I can now solve for AO, the amplitude of the output. I find that the amplitude of the output is equal to 0.1. Now I'll go and get the phase. The phase here is at negative 180. With this information, I can go back to my output plot and I'll draw this new signal. This one will be at the frequency omega high. It will be 180 degrees out of phase, and it will have an amplitude of 0.1. So this signal will look something like this. Notice I drew the signal starting to go down, so that this would be 180 degrees out of phase with a sine wave. Now that I have the individual outputs to each of these individual inputs, all I have to do is add them together. The final result will look something like this. I can find this output by adding together the value of the blue and the value of the red at every point in time. Once I've done that, I have the complete output shown here in purple to the strange input signal that we started with, shown here in blue. Now, as useful as that is, the principle of superposition gets really powerful when we combine it with Fourier's theory. Fourier's theory says that any kind of a wave, of any sort or any shape, can be broken down into a sum of a series of sinusoids. You may have used this theory before by using something called an FFT, or a fast Fourier transform. A Fourier transform is an approach to break up any kind of a wave into its individual sinusoidal components. The FFT, or fast Fourier transform, is a computationally efficient algorithm for figuring out what are the sinusoidal components of a complex wave. The output of a Fourier transform is a plot with frequency on the x-axis and amplitude on the y-axis. When we apply a Fourier transform algorithm to a wave, the output is a plot with a number of spikes or bars showing the amplitude of the different components of the wave at different frequencies. This result is telling us that if we add up sine waves at various frequencies at the specified amplitudes, we will get an output that is a wave of our original signal. So what does this have to do with the superposition principle? By using Fourier together with the superposition principle, we can find the output signal of any kind of wave input. What we do is we first apply an FFT or other Fourier transform algorithm to the input wave signal. What we get out is the components of the wave. Next, we compare these frequency components to a Bode plot of the system, and we get out a gain and a phase for each frequency component. Once we know the gain and phase for each frequency component, we can apply the superposition principle. The superposition principle tells us that we can add up each component to get out our final output. By combining the Fourier transform, our knowledge of a Bode plot, and the new superposition principle, we can find the output for any kind of input wave that we can dream up. So far, we've only talked about linearity. The other important system property that lets us predict the system output for any kind of input is called time invariance. Let's talk about time invariance now. Time invariance means the time that the input is applied only affects the time the output starts and nothing else. For example, we know that a step input looks like this. And we know that a second order step response might look something like this if it is underdamped. Now, let's suppose that the step input was not applied at time equals 0, but was instead applied at time equals t. What would the system output look like? If the system is time invariant, then the output will look like this. In other words, the output will look exactly the same, except that it will start at time equals t instead of starting at time equals 0. Now, maybe the property of time invariance seems obvious to you, or maybe it seems that this would not be very useful to know. But let me show you why this is useful and interesting. We can combine the time invariance property with the linearity property to easily figure out more complicated inputs. Let me give you an example. In our Slinky lab, we tried to give the Slinky a ramp input, which looks like this. But since our hands cannot just keep increasing in height forever, our actual input looked something like this. We increased in height at a constant rate for a time, but then we stopped increasing when our hand got to the highest height. How could we predict the output of the Slinky to an input like this one? The first thing we need to do is recognize that this input is the sum of two other inputs. This input is the sum of a typical ramp input like this one plus a second ramp input that looks like this one. Here, the slopes of these two blue ramp inputs are exactly opposite of each other. So when we add together the value of the two blue ramp inputs at every instant in time, we would get the purple input. The first ramp input is applied at time 0, and the second input is applied at time t. Because we know that the system is linear and time invariant, we can figure out the output to this by first figuring out the output to the first ramp, then figuring out the output to the second ramp, then delaying the second ramp output to time equals t. Finally, we apply the superposition principle by adding up the outputs. For example, if we know the time constant of the system, we can know the response to the first ramp input. For a second order system, the response to the first ramp might look like this. The response to the second ramp might look like this. Now we can find the complete response to the system by adding up these two red lines at every point in time. Note that this shortcut to finding the output of a more complex input is only possible because the system is linear and time invariant. In class, we'll be practicing doing this practically, and later on in class we will learn how to determine from the equations of a system whether it truly is linear and time invariant.